Okay, so welcome back to another video. So in today's video we have the limit as alpha approaches infinity of the integral from 0 to 1 of 1 divided by 1 plus x to the power alpha dx, and then that entire expression has the power alpha itself. Okay, so I like to define a function in terms of alpha of the inside. Specifically, let's define f of alpha equals 1 divided by 1 plus x to the power alpha, and with a little condition such that with the absolute value of x is less than 1. Okay, so then this has to imply that the limit as alpha approaches infinity of f of alpha, with also the condition that the absolute value is less than 1, so it actually has to equals 1. Okay, now now that we established that, now let's actually define this entire expression. Well, specifically the f of alpha is still contained in this integral, so that means the limit as alpha approaches infinity of the integral from 0 to 1 of f of alpha, and then dx, and I should have wrote this down, but I'm going to like capital P equals this expression here with the function in terms of alpha, f of alpha. And now I can actually just use our rules and we can actually move the limit inside of the integral. So it's the integral from 0 to 1 of the limit as alpha approaches infinity of f of alpha dx, which is simply, we said that that's equal to 1, so that means it's just basically the integral from 0 to 1 of dx. You evaluate this explicitly, you just get that it's 1. Okay, next. So let me define I of alpha equals to this integral from 0 to 1 of f of alpha. Okay, and this has to mean that P, we define capital P is equal to this expression here. P is equal to the limit as alpha approaches infinity of I of alpha, and then don't forget it's also with the power alpha from our given before. So this would mean that this is equal to, where we set I of alpha is equal to this integral, which was equal to 1, and then as it tends to infinity, so this is just simply 1 to the power infinity, which it's just equal to 1. Okay, let's note something here for a sec. Let's note that we're going to be using Euler's constant. So we know that the general formulation for Euler's constant is depending on what your variable is tending to, so in this case alpha tending to infinity, so Euler's constant is defined as 1 plus 1 divided by alpha raised with the power alpha, which is equal to e. Okay, so with this, let's actually given our pieces, let's actually rewrite this differently. So okay, that means P is going to be equal to, capital P is going to equal to the limit as alpha approaches infinity of, now I actually want to, from our P from here earlier, so what I want to do is I actually want to add and subtract one of the inside parentheses. So 1 plus I of alpha minus 1. And then I actually want to rewrite our power alpha a little bit differently. So what I'm going to do is I'm actually going to multiply and divide I of alpha minus 1. So this means we have this minus 1, and then this is being divided by I of alpha minus 1. Okay. Now, using our rules of exponents, I can actually just move our denominator of the exponent inside to into the inside expression. So simply, this is the same as alpha approaches infinity. We write this in brackets So then this will be 1 plus I of alpha minus 1, and then with the power of 1 divided by I of alpha minus 1, and then that's in parentheses, and then with our power from the numerator here, I times I of alpha minus 1. Okay, so notice that this is actually, the inside expression is equal to Euler's constant, E. If you want to check this yourself, how about we use our general formulation for what we define as alpha approaches infinity. If alpha was to approach 0, then the formulation would be different here. If it was alpha approaches 0, then it would have been 1 plus alpha, and then the power is 1 divided by alpha, but here this is written differently. So if we want to see that this is equal to E, we can just see that if we let's actually say n is equal to our exponent. Okay, now I can actually just multiply I alpha minus 1 for denominator and then to both the numerator and denominator. So that means we have n I alpha. Oops. This is I alpha minus 1 equal to 1, and then and then simply I can just divide by n. So divide n, and then we get I alpha minus 1 equals 1 over n. Notice that we have the same situation of just substituting. If we let alpha equal n, let's say, so we can just replace I of alpha minus 1, that's for here, and then this is n is equal to 1 divided by I of alpha minus 1. Then we can see that this is Euler's constant. I'm just going to erase that because this is just work not necessary. So this means, and then we're taking limits, so meaning I can actually, the only limit we would have to take is just our exponent. So simply I can just move the limit to this exponent. So we're evaluating for e to the power of the limit as alpha approaches infinity of alpha multiplied by I of alpha minus 1. Okay, and pretty simple. Now we can actually just take the natural log of both sides. So ln of capital P equal to the natural log of e raised to the same thing as before, alpha I alpha minus 1. And then you can see that this is clearly the only thing we need to check is to evaluate this limit. Alpha approaches infinity of alpha multiplied by I of alpha minus 1. Okay, now that we have that, let's actually, so the next thing we're going to be doing is we're actually going to use a tool. Specifically, we'll be using the geometric series. So I think I got room here, so yeah, I got room. Geometric series is defined as follow. It is defined as 1 divided by 1 minus x is equal to this, the infinite sum from our starting index being n equals 0 of some x to the power n with the absolute value of x is less than 1. Okay, so now that we have that, then what we can do now is we can go back to our f of alpha and then actually define this in terms of a geometric series. Okay, so now that we have that 1 divided by 1 plus x to the power alpha, that's simply just the same thing as 1 divided by 1 minus, and then inside minus alpha or minus x to the power alpha, and then that's just equal to the summation, our infinite series from n is starting from our index n equals 0 to negative x to the power n, and then to the power, or I got that backwards, that's supposed to be an alpha here, and then to the power n. And then just distribute the n to the inside, and so we get that it's the summation n equals 0 of -1 to the n, since n is being distributed here as a factor as well, and then x with the power of n times alpha. Now that we have that, then we can go back to our I sub alpha right here, and then just substitute with our series. So now we have I of alpha is equal to the integral from 0 to 1 of our series, and is equal to 0 of -1 and then multiplied by x to the power n times alpha dx. And then we can use our little rule of our rules of series, where we can actually just move this the series outside of the integral, and -1 to the power n is just a constant, so that itself that I can actually move that outside as well. So this is the series n equals 0 from of -1 to the power n, and then the integral of 0 to 1 of x and alpha dx. The light's not blinding? That's good. Yep. Okay. And then now we can just, now the only thing we can do is we can actually evaluate this definite integral over here. So let's see, let's do that. 0 to 1, x to the power n times alpha. Both n and alpha are both constants. So this means this is, so I just add 1 and then divide by that, the power. So it's n times, or x to the power of n alpha plus 1 divided by n alpha plus 1, and then evaluated from 0 to 1. And notice that if I plug 0 for x, then the whole term becomes 0. But if I plug 1 to any power, it's just always going to equal 1. So therefore we have that it's 1 divided by n times alpha plus 1. So we have that, and then we can substitute this back into our integral. So let me reiterate that I of alpha is equal to this, our sum, our infinite series, n is equal 0 of -1 n, and then multiplied by the power of, or multiplied by n, 1 divided by n times alpha plus 1. Let me simplify this out. And then we have -1 to the power n divided by n alpha plus 1. Now what I can do is I can actually rewrite the index. So what I want to do is, let's actually change the index to equal 1, but I have to evaluate this at 0 if I want to preserve its equality. So this means I can write this, if I were to evaluate at n equals 0, so this means n equals 0, so -1 to the power 0 is 1, and then 0 times alpha is 0, then plus 1 is just 1, and then plus, and then rewriting our index such that our starting index is n is equal to 1 of -1 to the n divided by n alpha plus 1. Okay, so far so good. So now that we have that, I can now, going back to what we have here, the limit as alpha approaches infinity of alpha times I sub alpha minus 1. Now I can just substitute what we evaluate for I of alpha. So now we write this as the limit as alpha approaches infinity of alpha multiplied by I of alpha, which is here 1 plus the infinite series at n equals 1 of -1 n divided by n alpha plus 1, and then minus 1. And then I'm going to clean this up a little bit. So this means we have 1 minus 1 is 0, and then I can just distribute the alpha. Therefore we have the limit as alpha approaches infinity of now I'm actually going to move the -1 to the n outside. Well, not really outside, but just so it's a product. So this means, in other words, I can just write this as infinity n is equal to 1. So it just have -1 to the power n, and then just move the alpha in place of our -1 to the power n. Okay, nice. So now let's actually take the limit as alpha approaches infinity. So what we're really focusing on is just this term in particular of our product. So we're going to observe that the limit as alpha approaches infinity of alpha divided by n alpha plus 1, we get that it's an infinity over infinity indeterminate form. So what I can do is we can actually take L'Hopital's rule, so and then take the derivative of the numerator and denominator in respect to alpha. So simply we just get the limit as alpha approaches infinity of 1 divided by n, but you know there is no alpha in this term, so simply the limit is just simply tends to just 1 over n. Okay. So now now we can just substitute our evaluated limit for alpha. So therefore we have so far, let me actually reiterate that we still have ln of p, which is equal to our series n is equal to 1 of now it's -1 to the power n divided by n. Okay, and now here's a little note that we're going to use, and we'll be finished solving this problem pretty soon. So now note that the natural log of 1 plus p, you can write this as its Taylor series. Specifically, you can write this as the negative summation from n is equal to 1, and then the upper index infinity of -1 to the power k, and then multiplied by p to the power k divided by k. Okay, so then we can write. So notice that in this case, for what our infinite series we're focusing on, p is equal to 1. So that means we substitute p into here, and since this is a positive series, not a negative, so I have to multiply the negative to the opposite side of here. So this means this is negative, or first let me write the series first. Let's write so the series, infinite series from n is equal to 1 to infinity of -1 to the n divided by n, that's equal to the negative natural log of 1 plus, we said that p is 1 to get the same matches here, so this is the negative natural log of 2. You could rewrite this, move the -1 factor back to the exponent here using our natural log rules, and then you get the natural log of 2 to the -1, which is the same thing as the natural log of 1 over 2. And now the last thing to do is, now that we have ln of p equals ln of 1/2, now you could just take the e base, so e to the ln of p, and then equal to e to the ln of 1/2 to simply get that p is equal to 1/2. Oops, messed up there. P is equal to 1/2. And we are done. Let me just circle this in black to reiterate. So therefore the conclusion is, we have that we define, I forgot to define it here earlier, but this is supposed to be p. P is the limit as alpha approaches infinity of the integral from 0 to 1 of f of alpha, where we define f of alpha is equal to 1 divided by 1 plus x alpha. And with the power alpha, I forgot to write that, but it comes later in the steps. The general answer to this problem is that the limit is equal to 1/2, and done like so. It's very nice, right?